Hello, everyone. My name is Jeff Hansen. Today, I would like to talk to you about the Portend project. We are about flexible and extensible drift monitoring in machine learning systems. The markings. All right, so the main idea is that early detection of machine learning performance degradation is key to mission success. We all know that ML models can be very powerful, but they're also very brittle too. Because of this, unexpected inputs can lead to unexpected behavior. Often systems do not know when they're performing poorly. They're getting inputs, they're producing results. Suddenly they could be producing wrong results. And in the worst cases, this can lead to model failure. It can lead to failed missions, loss of performance, and potentially loss of life. So what Portend provides is a suite of tools that enable model developers to craft components and agents that can monitor and alert on these unexpected inputs. This will enable these systems to take alternative actions or potentially schedule retraining when model performance is degraded. So the idea of brittleness is that every model has sort of an effective domain, an area where it performs well. And these are areas where the inputs are similar to the samples that were used for training. So for example, if we have a system that's operating on aerial imagery, as long as the system is receiving inputs that are similar to its training set, it's going to work well. But if there are changes in the environment, for example, now there's flooding when there wasn't when we were doing the training, then suddenly things aren't going to work very well. This can lead to misclassification. The model is going to tell us incorrect answers. It's going to be unable to tell when it's doing these misclassifications, and often there's what we call a digital cliff effect, where a little bit of drift is okay, the model still performs, but then at some point there's a sudden drop off where suddenly we're in an area where we're not okay at all. Now the current sort of approach is to sort of drift and this out of domain detection and management are concept drift and data drift. So concept drift is when our labels change. That is, maybe we have a detector that distinguishes between cars and trucks. But now later on we decide that, well, some of these things that we thought were cars, now we're going to start calling them trucks. But there's also data drift where slowly over time the features of cars or the features of trucks change over time. And now our old detector is unable to adequately determine between cars and trucks anymore. But there can also be simply changes in environment. If I'm looking at that aerial imagery, where I've trained my model on one set of aerial imagery, but then I'm going to go deploy it in a new area or an area where changes in the environment have changed, and so this can also cause models to degrade. Now, to manage this drift, systems must be able to detect when drift has occurred, has to be able to potentially schedule downtime for training, or be able to take mission actions to mitigate this drift. Now, model retraining is not always an immediate option because maybe the mission is too urgent. We have to do the mission now. Maybe there isn't relevant training data available to do the training, or maybe it's just too costly to do the training. So Portend is providing a solution that's looking at early detection of drift and out-of-domain data. So the basic idea is that we provide a set of tools that allow a model developer to generate monitoring and alerting components that can be plugged into the operational system. So the Portend system will take the ML model that we're deploying to the system, as well as a set of test data, generate a set of drifted images from a drift library set, generate those monitoring alerting components, and plug those into the system. So basically, drift planning is a form of sensitivity analysis. The idea is to try to figure out how well a model reacts to predicted changes in drift. So because we have these drift inducers, we're able to sort of dial up the amount of drift in the data and see how the model reacts to it. Now, drift planning happens at sort of two stages. There's model development, where I'm doing the drift induction, I'm assessing the models, I'm creating these monitors, and then there's model use, where I've taken the model, the inducer, the sort of the detector I've created, I'm plugging that in the system, I'm monitoring the system, and I'm generating alerts. So one way to think of this is Portend is a way to provide what we kind of think of as guardrails for ML. So while you're in that effective domain, everything's fine. When you head towards one of these guardrails, maybe a flooding guardrail that alerts when we get to flooding area, or an earthquake damage guardrail that alerts when we get to earthquake damage, or a seasonal shift when, like, maybe we've trained on summer imagery, but we're going into fall or winter, that allows the system to avoid kind of falling off the cliff, so to speak. Now, some people may ask the question, oh, well, no, why don't I just use the drifted data to extend my model? And that's great. You can do that and make your effective domain larger, but then you still have the risk of falling off the cliff, because now you just have all you've done is sort of move the cliff edge, so to speak, and now you have a new place where I'm falling off a cliff. All right, so this is kind of an operational overview of Portend. So we have some sort of set of training data that builds the model, that gets deployed to the system. We have some test data. We have some drift specifications for what types of drift that we care about for the particular mission in which we're going to deploy the system. And we have a set of drift libraries. These could be for image data, they could be for time series data, they could be for audio data, text data, or whatever. In this talk, I'm going to be focusing mainly on image data, but the Portend system is not necessarily limited to image data. All right, so in usage, there's kind of two main users of the system. There's the model developers, which are the main users that work with Portend directly. And those are the ones that use the Portend toolset to create these monitors and alerts. And then there's the operational users who use the deployed systems, and they interact with the deployed monitor and alerting component. And those allow the operational system users to detect when drift occurs and take these alternative actions. So the Portend toolset is composed of two main tools. There's the drifter and the predictor. So what the drifter does is it takes a base data set, whether it's image, text, audio, whatever. It takes an experimental configuration over what types of drift that we would like to induce in it, and it generates a data set with drift. The other tool, the predictor, takes the base data set, the drifted data set, some configuration metrics on what types of metrics we want to examine, and the trained model, and then it will run the model over both data sets, produce some prediction results, some prediction metrics, and those provide the basic elements that the data scientist needs to configure and tune the detector. Okay, so this is a look at the library, drift library for image data. So what the inducer does is it will take, say, an input image of maybe an aerial view of a city area. If I apply the flood inducer, it will make that look like it's flooded. If I employ the fog inducer, it will make it look as if we're in a foggy area. Other inducers that we are working on or plan include earthquake damage, season changes, and war damage. We have a set of some of our collaborators that we've been working on have sort of reviewed our drift conditions and have stated that they're mission relevant to them. All right, so looking at a more detailed example for image drift. So what we would do is we would take our reference images, apply the drifter to it. We get these drifted images. We test those set of drift detection metrics for sensitivity with the drift from the drifted images, look for changes in the metrics versus how much drift we've induced, test those metrics for sensitivity to generate the output of the trained model. So the drift plan example going on, we finally take those drift metric values and the model performance values to predict how much degradation occurs as a function on the different metrics. And that will help us, the model developer and domain expert, generate the action threshold, so the point at which the system will alert and say, hey, there's too much drift, we better do something about it. All right, so we are actually working with another project here at the SEI, the FEMA project, and what they are looking at is something called the FEMA scenario, and in that scenario, we're basically imagining that there's been some flood or other disaster, and there's some drones that have to deliver life-saving supplies to people stranded in the field. We assume that these drones are capable of flying the mission autonomously without support, and that we're flying in a GPS-denied environment, so the drone has to be able to navigate by means other than GPS. So specifically, they're navigating visually with a down-looking camera that's compared against a set of reference map images to find its position. And we're assuming it's sort of severe flooding in some areas may make the operational area look very different from the map area, which could lead to potential localization errors or localization failure. So what we bring to the FEMA scenario is the ability to sort of replan when we lose localization. So you can think of us as this area here on the left, the little house icon, is to where we're launching our drones. The white line is our planned route. The drone is moving along the planned route at some point where the X is. The Portend monitor detects the monitor is failing. There's too much flooding. I can't get any visual reference with the ground. So the monitor alerts, and the drone backtracks to a known safe location, maybe using a backup inertial navigation. And then the drone can choose to find an alternative route to the target and then eventually make it to the target. Here are some experimental results using data from the FEMA scenario. So we have on the graph is you have the predicted model accuracy on the y-axis. When we have the extent of drift, this is looking at fog drift. So the x-axis is basically as we turn up the dial on how much fog drift we have. And each line is for a different point on the map. So it's looking at how accurate am I getting localization information at different points in the map as a function of the amount of fog I have. And what I see is at many locations, we get a sort of a rapid decrease in performance, error increases, and when we go below that sort of dotted line there, that's when we say that there's too much error to get an accurate location. But we also see, interestingly, that some locations may be more resilient to this kind of error as well. All right, so looking at project contributions, we've kind of generated an easy-to-use tool set to generate monitors and alerts for drift. It's easy to configure for different scenarios. There's a simple configuration file. We support for different data modalities, including sort of image, time series, audio, whatever you want to bring to the table. And we can export metrics and thresholds for ML pipelines to detect and generate alerts on drift. It's extensible and flexible for different ML needs. It can support raw models as well as composite detection systems. For example, the localization algorithm is actually a composite algorithm where the ML part is a piece of a more complex algorithm. We provide support for adding custom data sets, custom drift functions, custom drift detection inducers or metrics, And we provide a base library of drift generation functions for images, including fog, flood, and earthquake. Sort of our next steps is to, we've kind of just started working on the earthquake drift inducer. We're looking at sort of designing and implementing automatic threshold generation to make it even easier for data scientists. Right now, the data scientist is generating these thresholds, so we'd like to make that automated. Looking at integrating sort of new library and monitor and alert detection to the tool set, and validating the end-to-end workflow with the FEMA scenario that I introduced. Some of our potential collaborators, we've a couple people, number of organizations who expressed interest, including the Air Force Safety Center, the Air Force Nuclear Weapons Center, Air Force Research Lab, and then we have a couple that we've had closer talks with, including the Air Force Academy AFWERX and Air Force Hypersonics. And this is our team. There's myself, Lena, Sebastian, Gabe, Eric, and Dave. Thank you very much, and if you have any questions, please bring them to the research review on November 8th. Thank you very much.